Greetings. My name is Devansh, and this video consists of a presentation on nuclear fusion energy. Nuclear fusion harness the power of stars. These are the contents of this video. What is nuclear fusion? When two nucleuses fuse into one bigger and stable nucleus, they lose some mass, which is transformed to energy and can be found using Einstein's equation E is equals to mc square. For fusion to occur, they have to overcome electrostatic repulsion of the nucleus. It can be achieved at extreme conditions such as high temperature and high density. This energy will be harnessed in nuclear fusion power plant. Nuclear fusion happens in stars. Nuclear fusion is not new science. It has been around since 1915, but the tricky part is to get more energy out than we put in. Nuclear fusion power plants are futuristic. Nuclear fusion is the latest form of energy to be commercialized. This is the nuclear fusion we will talk about in this video. Deuterium plus tritium is equals to helium plus neutron and 17.59 megawatt electron volts. This is the fission reaction in power plants. Neutron plus uranium is equals to barium plus krypton and 3 neutrons and 200 mega electron volt. So roughly 12 fusion of deuterium and tritium is equals to 1 fission of uranium. Problems we face. The major source of electricity is through fossil fuel, and about 60% of global need is fulfilled from it. And nuclear fission, about 11.1% of global supply. And there are some sustainable sources such as wind, which contributes to 7%, solar 4.5, and hydro contributing 2%. All the current sources of electricity have their disadvantages, such as fossil fuels are limited and the demand is increasing with increasing population. So fossil fuel will run out sooner than later. There's about 1.06 trillion tons of fossil fuel left, which would last around 132 years. Burning of fossil fuel is harming our planet, and thus, and they releases toxic and greenhouse gases, which causes global warming and air pollution. Nuclear fission uses uranium, which is 48th abundant element, and that is limited to. If we keep on using uranium, we're going to run out of it by the end of the century. Uranium is even difficult to extract, and a nuclear meltdown can be very dangerous. It creates nuclear waste which lasts around thousands of years. Solar panel lasts around 20 to 30 years. They need to be renewed after this, for which overmining must be done. We need to find ideal location for wind and hydropower plants, and sometimes those places are remote, so it's difficult to transmit the energy or the electricity. Prices of electricity is highly rising, and about 1 in 10 person people do not have access to electricity. A new source of energy is desperately needed, and nuclear fusion solves all of these problems. Advantages of nuclear fusion. It is generated from deuterium and tritium, which are isotopes of hydrogen. Deuterium is found in seawater, and tritium is generated from lithium fission reaction. So, a bottle of seawater and 1 gram of lithium will be able to supply electricity for a family of 4 for a whole year. The reaction creates about 4 million times more energy than chemical reactions such as burning coal, oil, or gas, and 4 times as much as nuclear fission at equal masses. 1 gram of nuclear fusion fuel creates equivalent energy to 8,000 liters of heating oil. Everyone will have access to cheap and abundant electricity. It produces virtually no harmful gases or air pollutant. No long lived nuclear waste has been created, unlike nuclear fission. There is no risk of meltdown, it is safe and environmental friendly. There are about 422 nuclear fission power plants, which contributes to 11.1% of global supply. According to theory, 600 nuclear fusion power plant can contribute to 20% of global needs, which is 21% more efficient than nuclear fission outcomes. Incentives. If nuclear fusion have such advantages, what steps are we taking to make it possible? There have been many attempts to harness fusion energy. Some of the famous attempts and events will be discussed in this video. There was an energy summit in 1985 in Geneva, in Switzerland, where Ronald Reagan and Gorbachev met and decided to launch ITER project, which is huge international collaboration with aim to create clean energy for peaceful purposes. 5 members: China, European Union, Japan, Russia, and United States collaborated to make it possible. Later, India and South Korea joined in. Now, scientists and engineers from around 35 countries are collaborating to make this decade-long project possible. National Ignition Facility. National Ignition Facility holds the strongest lasers in this world, and with help of these lasers, they were able to ignite a pallet of fusion fuel. On July 2023, they put 2.05 megajoules of energy and gained 3.88 megajoules, which is a gain of almost 1.9 in fusion torque. This was a breakthrough. The project confirmed that nuclear fission can produce more energy than consumed. Ever since this experiment, NIF keeps conducting more experiments like this to maximize the gain. The current highest gain is 2.36 in fusion torque in February 2024. NIF NIF is an inertial confinement. They uses pulses from superpower lasers. Inertial confinement is based on inertia. They compress the pallet as fast as they can in billionth of a second. While the output was 3 megajoules, which was sufficient to boil 30 cups of coffee, we need more prominent gains and on larger scale. ITER, International Thermonuclear Experimental Reactor. ITER is the star of the show. ITER, which means the way in Latin, is taking on a challenge to create nuclear fusion reaction on a scale of power plant and show the feasibility of nuclear fusion to mankind. ITER is located in France. It is the largest nuclear fusion reactor in the world. It seeks to have a gain of 10 in fusion torque, that is an input of 80 megawatts in thermal power and output of 800 megawatts in output power. ITER is an experimental reactor and is not making commercial electricity. ITER is designed for technology needed to make commercial fusion reactor. If all goes according to plan, it will be the last step before we could commercialize fusion energy for electricity. ITER uses magnetic confinement called tokamak. Wendelstein 7X, made in Planck Institute of Plasma Physics in Germany. They use magnetic confinement like stellarator, which we'll discuss later in this video. It is a smaller project in comparison to ITER, but uses different method. Private initiatives. Some private companies like Gauss Fusion and Helion are trying to achieve nuclear fission. Their approaches are different, and they're able to produce electricity from it as the scale of the project is smaller than ITER. For example, Helion is trying to use magneto-initial confinements. Tokamak and stellarator, the heart of the nuclear fusion power plant. Tokamak and stellarator are designs of main component of nuclear fusion power plant. This is where fusion will be occurring and energy will be produced. This is a brief history of tokamak and stellarator. Tokamak was designed by Soviet Union and was invented by these four scientists collectively. The first tokamak was built in 1958. Lyman Spitzer, an American astrophysicist, developed a stellarator design in Princeton University in 1951. How is stellarator different from tokamak? Stellarator have this very complicated shape, while the tokamak had this axial symmetric torus. The shape of stellarator is designed such that it's quasi-symmetric. The quasi-symmetric will help it reach equilibrium faster compared to tokamak, but ITER decided to go with tokamak design as stellarator will be much more difficult to build on such a big scale. ITER engineers believe that it is a question for future generation to solve, which will be more beneficial, stellarator or tokamak, or some other design. Since ITER is the first power plant sized fusion reactor, they have to start somewhere. It will be a question for future to decide which design would be best as per efficiency, cost, and efforts to build. Working. In fusion, resulting nuclei have less mass than the sum of two nuclei, and with Einstein's equation E is equals to mc square, we can calculate the energy released. The condition needed to fuse the nuclei are not found naturally on Earth. They are found in stars like our sun, which are made of 99% of plasma. Plasma is the fourth state of matter, a state where we heat up a gas to such a degree where the electron break free from the nucleus is called plasma. High temperature provoke high energy collision and therefore fusion. If we create a sustained plasma on Earth, we should be all set for making nuclear fusion. The problem is that it requires 150 million degree, which is 10 times hotter than the sun. This high temperature substance cannot be held in a vessel or a container of any material. So how do we store it? We induce a strong magnetic field, a cage, and store the plasma in that field. This is achieved using tokamak and stellarator, which are called magnetic confinement. So the plasma will stay confined. Plasma is electrically ionized, so it will remain in the magnetic field. According to Curie's law, the colder the magnet, the better its magnetic field will be. So the magnet in tokamak accelerator operates just about absolute zero, somewhere around 4 Kelvin, which is minus 269 degrees Celsius. ITER tokamak produce field nearly 12 Teslas, and Wendelstein produces 3 Tesla. They use cryoplant that circulates liquid helium and nitrogen to keep the magnet cold enough to act as superconductor, just according to Curie-Weiss laws. There is a minus 269 degrees Celsius of magnet, and just few tens of centimeter away, there is 150 million degree hot plasma. To experience this contrast, the temperature, there is 80 Kelvin shield between the two so that they don't influence each other's temperature. In the tokamak, the plasma is induced by heating the fusion fuel. So this is how ITER will heat the plasma. First, the changing magnetic field will create a high intensity electrical current, which will create resistance among plasma particles. This is called ohmic heating, which is used in toasters. Second is neutral beam injection. It involves shooting high energy particle into plasma. Third is by high energy electromagnetic waves. ITER aims to create a lot of plasma with tokamak. It will hold a volume of 840 cubic meters, while the Wendell still stores 30 cubic meters. This gain of 10 has never been achieved. So how is ITER aiming to solve that? The answer is the sheer size of ITER's tokamak. This is the largest tokamak in the world. This is the first tokamak with such dimension, which is 30 meters by 30 meters, which will enable the tokamak for self-heating. Once we get the plasma to a certain level, it will start heating itself. This is called ignition. This is the same reason why stars can burn for billions of years, only reaching after a critical point in temperature. In the nuclear fusion, the helium nucleus are produced, which we call alpha particles, which are charged and will remain inside the magnetic field of tokamak. The helium particle contains energy and will collide with other atoms with speed and transfer some kinetic energy, which will ignite this chain reaction. More energetic the plasma particles are, the more likely they are to fuse. Heat is just particle in motion. Faster the particles are moving, hotter the plasma. How will electricity will be produced from nuclear fusion power plants? This is where neutron shines. Neutron is electrically neutral, so it does not stay inside the confinement, and because of the energy they hold and the great velocity they were traveling with, they escape and are embedded with blanket, including cooling fluid, with 50 centimeter of steel in front of tokamak. There they are absorbed and will be using this energy to run turbines through heat exchange and thus producing electricity. Also, the neutron can be used to split up helium atoms into tritium, which will help us getting more fuel for fusion. This is a video of jet fusion reactor, Joint European Torus in UK. This is a breakthrough. They produced 69 megajoules in 5.2 seconds. These are the disadvantages. As discussed earlier in this video, they uses deuterium and tritium. Deuterium is found in seawater, but tritium is rare. There exist only 20 kgs of it, and only 100 grams of tritium is generated naturally per year. We can make tritium from lithium using fission reaction. Lithium is 25th abundant element on this planet and can be used until scientists find more efficient way to generate tritium. There's also some tritium available in fission reactors, moderate pool, which are filled with heavy water. These pool absorb the high energy neutron given off in the fission, and in doing so, they become tritium. Tritium can also be replaced by helium-3, which is abundant on Moon. Scientists are still looking for more substitutes. A solution for this is to make tritium surplus reactors. From today's perspective, it is the most complex power plant compared to others. But in future, we might come up with a solution to optimize it further and further. ITER project itself cost $22 billion, and making 600 of these worldwide would create an issue economically. The size of ITER. ITER project is a grand project. Before they could build the reactor itself, they have to make the components. So they make it near the reactor rather than importing from far away. Also, some components like colloidal field coil and cryostat, which is the enormous vacuum chamber which surrounds the reactor, are too big to transport on road. So they need to be make the building that would make the components. France need to make a separate road just for this project, which is called ITER itinerary. This road is in constant police surveillance to make sure goods are being transported on time. ITER requires power to make power. They are transmitted from 400 kilowatt transmission line, which is stepped down and distributed into different stations. Some stations require DC, so they need to make a industrial size power adapter. When can we accept the first plasma? When will the construction be complete? Construction began in 2006 and they expected it to be done by 2016, but the date is being pushed back multiple times. And they are expecting the construction should be done by 2025. At the present moment, they are 89% done. They need to make demo reactor, which is demonstrative reactor after the project, which is 50% bigger than the ITER, which will produce 2000 megawatts electricity, which will make commercializable electricity and will operate 24/7. This is not a showstopper, but it requires one more step in the process of commercializing. We don't know the correct way. There are magnetic confinements like tokamak and stellarator. There are initial confinements like laser and Z minus and X minus pinch. Scientists are still trying to figure out which will be more suitable. The current lead is taken by tokamak and stellarator as discussed in this video. We can't invest all the money and fate into one model of fusion. We need to optimize a model for production, and scientists are still arguing to find a better model. Think about invention of airplanes. We didn't know how the shape of plane would be until Wright brother made a concrete shape for it. Similarly, it will take time for science to create concrete shape for fusion reactors. Currently, they require more energy to do the experiment than they are able to produce from nuclear fusion. Until they build massive self-igniting and heating power plants, which require massive budgets and time, like ITER. Conclusion. Nuclear fusion is an amazing technology which will help us by providing cleaner and cheaper electricity. Mankind is still working to make it commercializable and optimize it, and indeed harnessing the power of star on Earth. This video concludes nuclear fusion, incentive in making nuclear fusion possible, confinements, and advantages and disadvantages of nuclear fusion. These are all the references. Thank you.